Hello guys, what's up? Okay, the moon is up, the sun is up, sky is up. Welcome to today's video, and we are going to be learning on the third problem of application of differential equation, which is a motion problem. Basically, we're talking about motion in terms of velocity, displacement, and acceleration. And let's dive into problem 3 right away. So suppose a rocket is launched with an initial velocity v0 equal to root 2gr, where r is the radius of the earth. Neglect resistance and find an expression for the velocity v in terms of the distance x from the surface of the earth. And the b part says find time required for the rocket to go 240,000 miles, approximate distance from the earth to the moon. So assume that r is 4,000 miles. Okay, so let's dive into the solution of these problems. I'm going to be using some diagrams to help us understand how to approach this problem. So let's begin. Now, to make this problem simpler for us, I'm going to draw the earth, I'm going to draw the moon. Okay, I'm going to draw the earth and I'm going to draw the moon, so we can actually get the picture of what is happening. So yes, some people's up is some people's down, and some people's down is some people's up. Weird, right? That's how the earth is. So assuming I shoot the earth like this, oh, my spherical beautiful earth, then the moon is somewhere here. Okay, then this is Africa from where I come from. I love Africa. Okay, and other continents, America somewhere here, Oceania, and so on and so forth. Now, the center of mass of the earth is somewhere here. Okay, and the center of mass of the moon is somewhere here. Then there is a line that links the earth to the moon over here. Is that okay? So the line from this point to this point is the radius of the earth. Okay, so I'll assume that Elon Musk's rocket is going to take off from this point. So this is rocket, it's about to take off from this particular point, and maybe it's going to be here as a satellite sometime in the future, and so on and so forth, and so on and so forth. So, and probably a few years later, or a few months later, or a few weeks later, or a few hours later, it's going to land on the moon somewhere. Okay, so this is the diagram we are going to use to picture and solve our problem. Now, our objective is that suppose this particular rocket is launched with v0 equal to root 2gr. So r is the radius of the earth, of course. So we should neglect air resistance. Then we should find the expression for velocity in terms of the distance x from the surface of the earth. Now this is the surface of the earth. We should draw a horizontal line or a tangential line to this particular point. This is the surface or the takeoff point of this particular rocket, and this is its trajectory until perhaps it may get to the moon in the future. But we want to see the equation that will describe the velocity, okay, in terms of the distance of this particular rocket and satellite from the surface of the earth. Now we are going to do that carefully, so follow me. Okay, it's something that you already know before. So Newton's law of gravitation. So according to the statement from Newton's law of gravitation, so follow me together. Newton says that the magnitude of force between two bodies is actually proportional to is actually proportional to what? The products, right, of the masses of those bodies. So let me say the mass of the Earth, then the mass of the rockets or the mass of the satellites, and it is inversely proportional to the square of the distance between them. So assuming the distance between the Earth and the rockets is represented by r, that's actually inversely proportional to the square of the distance between them. So this is the statement of Newton's law of gravitation. So the magnitude of this force is actually equal to a constant of proportionality, then the mass of the Earth, the mass of the satellites, over r square. So let me take this statement as my equation 1. Now we are going to be making some assumptions that are actually seeming cool and actually seeming fitting for this particular purpose, so that we can be able to simplify our problem. Now, in as much as we are going to be making some assumptions, sign convention is also very, very important here. So this particular question, we don't want to solve it using the vectorial approach as it is meant to be, but we can't do without taking note of sign conventions. So let me define my sign conventions here. Sign conventions. So I'm going to choose a reference point for defining my sign convention. The reference point is towards the center of mass of the Earth. Now, if the Earth attracts a body towards itself, the sign convention will be a positive. Okay, so a plus, we are going to use a plus to indicate an attraction towards Earth. Okay, then I'm going to use a minus to indicate a proportion away from Earth. Away. So an attraction towards Earth will be, for instance, like perhaps me feeling my weight. The Earth is actually exerting a force and I feel my weight, so it's actually going to be a plus in that case. So a proportion away from the Earth will be, for instance, the force which the rockets used to spin away from the Earth and probably attain its escape velocity. So that's the force that we are going to label with a negative sign. So having defined our sign conventions, I begin with my assumption. Now I want you to take note of this parameter r here. This parameter r here is actually going to be r plus x. And somebody will ask me, why is r plus x? So assuming the satellite has gotten to this point now, so you can call the distance from the surface of the Earth to this particular point x, okay, because we want to express it in terms of x, of course. So you now agree with me that from this point to this particular point is actually the sum of x and r, or r plus x. Okay, so at any particular point in time, r is given to us as the sum of r plus x, where r is the radius of the Earth and x is actually the distance of the particular mass or the satellite from the surface of the Earth. Is that okay? So let's continue. Having defined these conventions, now you're going to now assume, because we want to be able to find out what this constant of proportionality is. So to find out what the constant of proportionality is, first things first is that you're going to make an assumption. Okay, you're going to make an assumption. So when you're making the assumption, we will now introduce our sign conventions. So what assumption are we making first of all? The first assumption we are making in order to determine k is that at the surface of the Earth, right? At the surface of the Earth. So assumption 1, at the surface of the Earth, what happens to the satellite? The satellite feels a weight. Satellite feels its weight. Is that okay? And since the satellite feels its weight at the surface of the earth, then the force, the magnitude of the weight is given to us as mass of satellite times what? Gravity. Are we together? Mass of satellite times gravity. So the weight of the satellite is mass of satellite times gravity. That's the magnitude, and this is equal to k m e m s over r. R becomes r plus x all squared. But remember that since we are dealing at the surface of the earth, at the surface of the earth, this particular distance x becomes 0. Okay, look at it from the diagram. At the surface of the earth, so this is our origin. The origin is here, so x increases from this origin along. So the only parameter that will be contributing to r on the denominator is actually capital letter R, which is what? The radius of the earth. So having established this, our msg is equal to k mems over r squared. So ms cancels out ms, and we'll have that our k is equal to what? G r squared over mass of earth. Is that okay? So this is equation 1b. Now, since we have gotten k from initial conditions, the initial conditions being at the surface of the earth where x equal to 0 and where the mass of the satellite, or where the weight of the satellite is felt, and of course since the weight of the satellite is felt, our sign convention is still going to be a positive sign. It's still actually a positive, so it's plus. Why? Because the weight is attracted towards the earth center, so we're going to use a plus in that case. So when we do the cancellations and make k the summary of the formula, we have k equal to g r square over me. So we're now going to substitute this in equation 1. So substituting it in equation 1, we have that the magnitude of the force, okay, between two bodies is k, which is now gr squared over me, and we now have mass of earth, we now have mass of satellite over r squared. So if we do the cancellation properly, we'll have that the magnitude of force is actually, we now have mass of satellite, then g r squared over r squared. So you can call this equation 2. Call this equation 2. Are we together? Now let's move on. Now the next assumption that we are going to make, okay, feel me, next assumption that we're going to make is we are now going to make the assumption when assuming the rocket has already taken off from the surface of the earth. Now when this rocket takes off from the surface of the earth, if you remember your simple harmonic motion, or if you remember your second law of motion precisely, the magnitude of the force is proportional to the mass of the satellite and the acceleration with which the satellite is using to progress. And of course this force is actually directed away, okay, from the earth. So this force is a propulsive force that moves the satellite away from the earth, unlike the force that attracts it downward. Therefore, the sign convention will be a negative sign. So I now want to model a case from my equation 2, okay, when the satellite is away from the surface, the earth's surface. When the satellite is away from the earth's surface, the magnitude of the force, or the force this time around, the absolute value of the force, I'm not going to use the magnitude because we need to take note of the vectorial sign. The force with which it is moving is actually minus ma. Okay, remember our sign convention. So m is actually the mass of the satellite, a is the acceleration of the satellite, and acceleration is the rate of change of velocity. So we have mass of satellite dv dt. So this is equation 2b. So if you substitute equation 2b in equation 2 now, what you're going to get is, you now get minus ms dv dt is actually equal to ms gr squared over r squared, like this. So ms cancels out ms. So what we now have is dv dt is actually what? Negative gr squared over r squared. So we are now going to do some transformations. Follow me. Now I hope you understand why this minus sign came about. Remember, if you go back to where I defined sign conventions. Any force that is taking the rocket away from the earth, okay, that force is going to have a negative sign, okay, and the force that keeps it attracted towards the earth is going to have a positive sign. So that's why this left hand side, okay, actually now evaluates to minus ms times a according to Newton's second law of motion. Sorry. So as we keep solving, we now got dv dt is equal to minus gr squared. So I want you to remember something. Let's go back to the basics. That velocity itself is actually dx dt. Is that okay? So x means displacement. Is that okay? And the velocity is the rate of change of displacement. That means, for instance, if I make dt the subject of the formula, you're going to get dt is dx over v. Is that okay? So if you now carry this dt and put it back into this equation up here, you're going to get another expression for dv dt. dv dt corresponds to dv. Instead of dt, you have dx over v, and this will now be v dv dx itself. So from dv dt, another expression for acceleration is dv dt, another expression for acceleration is v dv dx, okay, product of the velocity and the ratio of change in velocity to change in displacement. This is another way of defining acceleration. So also you have to remember that r is actually radius of the earth plus x, okay, assuming that the rocket is, or the satellite is, some distance x away from the surface of the earth. So transforming this particular equation, what we now have is v dv dx is equal to minus gr squared divided by r plus x all squared. Are we good? Now if you separate the variables, of course this is variable separable, you will get v dv is equal to negative gr squared over r plus x all squared dx. Okay, now please, I hope you are not mistaking what constants and what variables are here. So in this equation 3, for instance, our constants are the likes of g and r. Okay, g and r are constants, then variables are v and x. So we have actually succeeded in what? Separating the variables. Now when we take the antiderivative, so we have integral of v dv is equal to integral of negative gr squared all over r plus x all squared, okay, dx. So I'm going to focus my attention on the right hand side, so don't be scared. It's very, very simple. Integral of v dv is equal to, first of all, take out gr squared. I left the minus sign there intentionally. Now have minus 1 over r plus x squared dx. Is that okay? So as usual, like we've been doing in the past, assuming you want to differentiate, follow me, you want to differentiate r plus x with respect to x, what are you going to get? Differentiating r is a constant, it cancels out, then differentiating x, you get 1. Is that okay? So d of r plus x is equal to 1 dx. Are you with me? So d of r is actually what? 1 dx. So anywhere I see 1 dx, I can actually replace it with what? D of r. Now look what happens when we do that. Now have v dv is equal to gr squared, then integral of, then minus. Now this particular place where there is a 1 dx, you can now replace it with what? D of r plus x. So this can still be minus 1, then you can now have d r plus x all over r plus x squared. So our integral is now of the form, integral of minus 1 over something d, something squared is something. Okay, so minus integral of 1 over something squared is something is just very easy, as if you were integrating minus something raised to the power of minus 2 d something. Is that okay? And this gives me minus something raised to the power of minus 2 plus 1 over minus 2 plus 1 plus constant of integration, right? I hope you still remember the law of integration. So this is minus something raised to the power of minus 1 all over minus 2 plus 1 is minus 1. So if this cancels out this, you just get left with minus something raised to the power of minus 1, which is 1 over something. So in other words, when you differentiate 1 over something, you're going to get minus 1 over something squared. So whenever we integrate this, we just want to recall, according to what we just proved now, that the integral of minus 1 over something squared d something is actually equal to 1 over something. Simple. So this whole integral here, you can see the something that we are talking about is r plus x. So when you integrate this side, you're going to get v squared over 2 and is equal to gr squared. Then when you integrate this whole side, you're just going to get 1 over r plus x. Is that okay? So this is what you're going to get by integrating the whole of this side. When you integrate the whole of this side, you're going to get 1 over r plus x. And you can try to differentiate 1 over r plus x with respect to x, and you're still going to get minus 1 over r plus x all squared. Now that we've done that, we now say v. Okay, don't forget your constant of integration plus c. So v squared is equal to what? We have 2gr squared all over r plus x plus 2c. Is that okay? So we can call this equation 4. Okay, now they gave us an expression for what? v naught. Is that okay? They said v naught is equal to root 2gr. If v naught is root 2gr, what are they trying to tell us? It means that when x is 0, are we together? When x is 0, that v is equal to what? Root 2gr. So if you plug this particular initial conditions into this equation 4, you will have v squared, so root 2gr squared, root 2gr squared is equal to 2gr squared. Anywhere we see x, we'll put 0 plus 0, then plus 2c. Let's just call 2c d for instance. Okay, let's 2c be equal to d. So if you simplify, of course, when you take the square of a root, the square and the root actually neutralizes themselves, leaving you with just 2gr on this side, and this will be 2gr squared over r itself. So r cancels out r, and you're left with 1r plus d. So the implication is that d will be 2gr minus 2gr, surprisingly, and this is equal to 0. So our integration constant in equation 4 is 0. So equation 4 reduces to v squared is equal to 2gr squared over, let me take it up, sorry, over r plus x. So in other words, our v of x is actually plus or minus the square root of 2gr squared over r plus x. So this is an expression, okay, of v in terms of what? This is an expression. This is from equation 4. Let me call this one equation 5. So equation 6 now is an expression of v in terms of x according to the first requirement of the question. So we've determined, so this is the equation for the velocity of the satellite or rocket launched x units from the surface of Earth. So at any particular x unit away from the surface of the Earth, we can determine the velocity by this equation. So this equation stands. Wow, one day I might actually send someone to the moon, or I'll go myself. Okay, let's continue. Now we have gotten v of x to be plus minus the square root of 2gr squared over r plus x. So the b part of the question, so let's just scroll to the b part of the question and see what it is. So the b part of the question says, find the time required for the rocket to go 240,000 miles, approximate distance from the Earth to the moon. So assuming that r is equal to 4,000 miles. So let's take note of the unit, 240,000 miles, and r is approximately 4,000 miles. Everything is taking us back to our equation 6. Is that okay? Everything is taking us back to equation 6. So from equation 6, now permit me to remove the plus and minus from equation 6. V is given to us as the square root of 2gr squared all over r plus x. Is that okay? Now you have to recall that velocity is the rate of change of displacement. V is actually dx dt. Is that okay? So dx dt is actually, let me distribute the roots. We have root 2gr squared over root r plus x, like this. So if we separate the variables, you're going to get root r plus x on this side, dx is equal to root 2gr squared, okay, dt. Okay, so we're going to take the antiderivative of both sides. So integral of root r plus x dx is equal to the integral of root 2gr squared, you have dt. So we're going to take this integral, and in taking this integral, of course consider the left hand side. Of course you want to consider the left hand side. So assuming you want to differentiate with respect to x, r plus x, when you want to differentiate this, you're going to get 1. So d of r plus x is actually 1 times dx, which is dx. So you can actually replace dx with what? 1 plus dx. Okay, now what we now have is integral of root r plus x. Instead of dx, we have dr plus x, and is equal to, then if you integrate this one, of course you have 2gr squared, which are all constants, integral of dt. So in this particular place, I have integral of root something d something, and integral of root something d something is not very difficult to solve, because integral of root something is something raised to the power of 1 over 2. So the something, so if you evaluate this integral, it will be something raised to the power of what? 1 over 2 plus 1 divided by 1 over 2 plus 1, and this is actually going to be 2 over 3 something raised to the power of 3 over 2. Okay, for short. So when we integrate something, the something, we are going to get 2 over 3 something raised to the power of 3 over 2. So this is the working on this particular, on the right hand side of the screen. So when we integrate roots r plus x, the r plus x, just like when we are integrating the root of s, the s, or the something, what we are going to get is 2 over 3 something, which in this case is r plus x raised to the power of 3 over 2. Okay, so this is for this left hand side, and equal to root 2gr squared. Then when you integrate dt, you're going to get t, then plus c. Okay, so this is another constant of integration, and we can find this constant of integration right away. So I don't think I'm keeping track of my labeling of equations. So okay, equation 6, that means this should be equation 7. Okay guys, here we are at equation 7, and we have an integration constant here to determine. So let's try to find the value of the integration constant. And to find the value of the integration constant, we are going to use the assumption that x of 0 is equal to 0. So somebody asked me, why am I using this assumption? Trying to tell me that the displacement of the rocket from the surface of the earth is 0 when t is actually 0 seconds. So you know, and when people shoot rockets to space, they used to be like t minus 9, minus 8, minus 7, minus 6, minus 5, minus 4, 3, 2, 1, 0. So at the point when t is equal to 0 and counting, just at the start, the rocket is still at the surface of the earth, and at the surface of the earth there is no displacement x. So x of 0 is equal to 0. So in this particular equation, anywhere you see x, you're going to put 0, and anywhere you see t, you're going to put 0. So you get 2 over 3 and r plus 0, 3 over 2 is equal to the square root of 2gr squared. Then you now have 0 plus c. So this whole stuff cancels out because of 0 as a multiplier. So c is now going to be 2 over 3 r raised to the power of 3 over 2. Is that okay? 2 over 3 r raised to the power of 3 over 2. So finally our equation is now going to be 2 over 3 r plus x raised to the power of 3 over 2 is equal to the square root of 2gr squared t plus 2 over 3 r raised to the power of 3 over 2. So this is our displacement time equation. Displacement time equation, and the objective is to determine t for some particular value of x. So if you make t the subject of the formula, you agree with me that you're going to get gently 2 over 3 r plus x raised to the power of 3 over 2 minus 2 over 3 r raised to the power of 3 over 2 divided by the square root of 2gr squared, like this. Is that okay? So this is the expression for t in terms of x, and we have to determine t, right, when x is 240,000 miles, and they said we should assume that r is what? R is what? 4,000 miles. So I'm going to leave you to substitute these values on your own and determine t. So you can pause the video now and try to do it by yourself. So I'm going to actually do it when you're done, so you can pause the video and try it now on your own. Okay guys, welcome back. I guess you paused the video and you saw it by yourself. So let's see what we're going to get together. Let's see if what you got corresponds with what I get. So the first thing I'm going to do is, since I'm giving my distances in miles, okay, I am going to actually convert this particular gravitational constant to a unit corresponding to miles per hour square. Okay, so how are we going to do that? So you should already know how to do conversion like this as an engineer. 9.81, okay, meters per second square, so corresponds to 1 mouse is equivalent to what? 1609.344, okay, meters. Okay, so this is the relationship between a mile and a meter. I think I still remember this on 609.344 meters. Then you now have 1 all over, you now have 1 hour squared is equivalent to 3,600 squared of seconds. In this way, is that okay? So 1 hour square is equivalent to 3,600 squared of seconds. So this is just the way I'm going to use to convert my gravity from meters per second square to miles per hour square. So miles cancels out, meters cancels out meters, so second, the denominator cancels out second square in the denominator. So if I rearrange, I'll have g to be 9.81 times 1 miles, okay, times the 3,600 now comes up squared all over, I have 1609.344. so if you evaluate this on the calculator, remember there is a hour in the denominator, so there's a hour, not just a hour square in the denominator. If you evaluate this, you're going to get 78999.64, and this is corresponding to miles per hour square. So this is actually an approximate value for the gravitational constant in miles per hour square. So what do we do with it? We're going to now use it in this particular equation over here, So we're going to use our g in miles per hour, our r in miles, x in miles, and so on and so forth. So to calculate t, you're just going to say t is, we have 2 over 3. Remember, it's r plus x raised to the power of 3 over 2 minus 2 over 3. We have r raised to the power of 3 over 2, and divided by the square root of 2gr squared, like this. So if we substitute all these values given to us, 2 over 3, we have r being 4,000 and x being 240,000 raised to the power of 3 over 2, and minus 2 over 3. R is what do you have? Still 4,000 raised to the power of 3 over 2, and all over the square root of 2. Our g is 7,8 999.64, then r squared is 4000 squared, and the answer should be in hours this time around. Okay, the answer is going to be in hours. If you do the derivation of the units, you're going to get it to be in hours. So let's just use our calculator to punch and see what we get. Let's use our calculator to punch and see what we are going to get. So punching with our calculator, we are getting T to be approximately 50.43 hours. So some people might just round it up to the nearest hour, for instance. So T is probably going to take us around 50 hours. Okay, if we round it up to the nearest whole number of hours. So this is actually where you call it an end for this particular problem. And if you check some advanced books, you discover that these values actually correspond to what they are meant to be. It takes about 50 hours, okay, for someone to travel with a particular escape velocity from the Earth to the moon. Okay, so this is the time it takes. So I'll let it be for now. I know this video has been long, but I hope you learned a lot. And don't be scared of the length, just know how to solve it, know the theories, know what you're supposed to do, know how to put them together, and you'll be alright. So there's still more problems to solve in applications of differential equations, and we'll see them in the next videos. So stay tuned, like, subscribe, share, hit the notification button to stay updated, leave comments, leave questions, and I'll attend to them when I see them. Okay, peace.